Hi and welcome to the presentation of my degree project, Performance Analysis of FRRouting. The Internet consists of a large number of distinct independent entities, called autonomous systems. The administrators of ANAs have full control over the set of IP prefixes owned by the autonomous system as well as its routers and links. These systems exchanges routing information consisting of IP prefixes through the Border Gateway Protocol. To facilitate this exchange of information, autonomous systems are often connected to an root server located at an Internet exchange point. Due to this, BGP is an important component of the Internet backbone infrastructure. In the picture on the right you see an illustration of how a root server may look like. BGP is implemented in a wide range of different software suites, where one of the most popular open-source alternatives is FRRouting, which is backed and used by the Linux Foundation. Given the large scale of the Internet network and how much we rely on it for our everyday lives, understanding the performance of BGP implementations is important for ensuring a well-functioning Internet. Here's the outline for today's presentation. We have a lot of cover, so let's jump in. So what's root server? A root server facilitates the administration of peering arrangements for networks connected to an Internet exchange point. By connecting to the root server, autonomous systems can replace some or all of the separate BGP sessions to their peers with one single session towards the root server. This hugely simplifies the work of network administrators and even give each autonomous system access to way more routes. The job of the root server is to collect prefixes from its peers, process this information and announce the optimal route to a specific destination back to all of its peers. To do this, the root server may use of the FRRouting software. In the figure on the right, you see an illustration of how autonomous systems connect to each other over a root server. As of today, there exists around 800,000 IP prefixes that are announced through BGP. Last year, this number grew by 6% year over year. Processing hundreds of thousands announcements after restarting the system process may take up to 10 minutes to complete. During this time, the optimal route towards a specific destination on the Internet may not be known, which impacts the communication in a negative way. The purpose and goal of this work is to quantify at what rate FRRouting is capable of processing BGP announcements. The results may be of interest for networking organizations, operators, and the open source community. To achieve the goal, we run a set of experiments where FRRouting processes BGP messages under varying network configurations. The results are analyzed to determine if there are any bottlenecks regarding FRRouting's capacity of processing BGP announcements. We also look at how different configurations of FRRouting impacts the performance of it. The results are then discussed in order to determine if there are any bottlenecks regarding the capability of FRR of processing BGP announcements under different configurations. Now to the methodology. To analyze the performance of FRR, we use the following metrics. First, we measure how many prefixes the root server receives from its connected autonomous systems. Next, we look at how many prefixes that is installed in the routing table of FRRouting. This is then compared to how many prefixes the root server is capable of announcing back to its peers at a network level. Regarding the benchmarking environment, we make use of two servers that are connected to each other through a switch. The first server, S1, runs the FRRouting software suite configured as an root server. The second server, S2, emulates a set of 24 BGP peers that advertises BGP announcements consisting of IP prefixes towards the root server at S1. The setup is illustrated in the figure shown on the right. The root server processes and announces the received prefixes back to all of its peers over the network. The network traffic between the two servers are captured with the Wireshark network analyzer and the captured data is parsed with a dedicated BGP parser. Captured network traffic is analyzed to get the number of prefixes FRRouting is capable of announcing back to its peers within a time span of 180 seconds. Simultaneously, the number of received prefixes at the root server are also recorded. As previously described, we make use of a single server to emulate 24 BGP peers that acts as autonomous systems. These peers are all emulated within the second server. To achieve this, we make use of EXA-BGP, which provides a convenient way to implement software-defined networking by transforming BGP messages into friendly plain text or JSON, which can then be easily handled by simple scripts. 24 EXA-BGP instances are run within the second server, but since every virtual peer operates under the same server, S2, we use namespaces to separate them, which makes it possible to assign the peers different and separate instances of network interfaces as well as routing tables that operate independently from each other. As seen in the figure, each peer is connected to a virtual switch within the second server. The switch is in turn connected to a network interface on the server running FRRouting. The root server running at the first server is configured as follows. 3 different configurations of FRRouting are used. These configurations control how filtering of received prefixes is applied at the root server. The first configuration do not apply any filtering of prefixes. Next, for our second configuration, we filter out a set of 500 prefixes that are not advertised by the peers. In the third configuration, we filter out 500 prefixes that actually are advertised by the peers. The purpose of these configurations are to research how the number of announced prefixes, by the RS, changes depending on the filter configuration. To ensure a scientifically accurate benchmarking methodology, the BGP peers announces prefixes towards the root server during a time span of 180 seconds. Benchmarking is done for a varying number of different peers, and to ensure scientific accuracy, an average from 10 benchmarking rounds are recorded for each set of peers and filter configuration. Now to the results. In the tables on this slide you see the number of received, installed, and announced prefixes for each set of peers and filter configurations. When examining the tables, we notice that the number of received prefixes are slightly higher than the number of installed prefixes. But the number of received and installed prefixes are way more than what has been announced by the root server on the network, as seen in the last table. This shows that there exists a bottleneck in FRRouting when it comes to announcing prefixes on the network. This data is later visualized in a set of graphs. Here we present how much the data fluctuates in between the 10 benchmarking rounds. Fluctuation is calculated as the percentage difference between the benchmarking round with most and least recorded prefixes. When examining the fluctuations in the 3 tables on this slide, we notice that our benchmarks of received prefixes resulted in the lowest fluctuation rate. Announced prefixes, on the contrary, shows a considerably higher rate of fluctuation when compared to both received and installed prefixes. The fluctuation of announced prefixes is at the most 345 times higher when comparing it with the fluctuation of received prefixes with the same number of peers used in the benchmark. The considerably higher fluctuation of announced prefixes further strengthens the results that our root server seems to not be able to announce prefixes at the same rate as it receives these prefixes from its peers. Here, the presented data is visualized in a set of graphs. On the left, we have the average number of installed prefixes for each filter configuration compared to the average number of received prefixes. Likewise, on the right we have the average number of announced prefixes for each filter configuration compared to the average number of received prefixes. When examining the graphs, we see that the number of installed prefixes is very close to the number of received prefixes. But the number of announced prefixes is several magnitudes less than the number of received prefixes. On this slide, you see a comparison between the 3 filter configurations for installed and announced prefixes. It's once again seen that installed prefixes is more than announced prefixes. Also, the second filter configuration seems to perform the best when it comes to announcing prefixes. For installed prefixes, all configurations are roughly the same. Lastly, we visualize the fluctuations for all benchmarks. On the left, we have the fluctuation of installed prefixes compared with the fluctuation for received prefixes. Likewise, on the right, we have the fluctuation of announced prefixes compared with the fluctuation for received prefixes. The key takeaway is that announced prefixes causes the highest fluctuations. For announced prefixes, the first configurations that do not filter prefixes resulted in the lowest fluctuation. Now to the discussion. The data presented clearly shows that our root server running FRRouting is not capable of announcing prefixes at the same rate as it receives these prefixes from its peers. The number of prefixes the root server announces within 180 seconds is consistently several magnitudes less than the number of prefixes it has received from the peers as well as installed in its routing tables. In addition to this, the results are further strengthened when examining the fluctuation data for announced prefixes. Here we notice a considerably higher fluctuation rate across all benchmarking rounds and set of peers when we compare these results with the fluctuation for received and installed prefixes. Additionally, the fluctuation rate for announced prefixes increases when applying filtering of prefixes, meaning that the second and third filter configuration, that apply filtering of prefixes, shows a higher fluctuation rate compared with the first filter configuration that does not apply any filtering of prefixes. This can potentially show that the filtering of prefixes at our root server leads to an increased load on the FRRouting software suite, since it must examine each prefix it receives and take action according to the rules specified in the filter configuration. For example, when looking at the CPU utilization on S1 during the performed benchmarks, we notice that the BGP daemon is utilizing around 40% of the CPU when the first filter configuration is applied. However, as for the two other filter configurations that do apply filtering of prefixes, the CPU utilization increases to around 150%, meaning that filtering prefixes is more computationally heavy for FRRouting to perform compared with not filtering prefixes. As discussed in the previous slide, the rate of fluctuation for announced prefixes increases when the root server is configured to apply filtering of prefixes. However, when examining data as well as the figures, it can be seen that the first filter configuration, which does not apply any prefix filtering, resulted in the least amount of installed and announced prefixes. This is noteworthy since we previously discussed why filtering of prefixes resulted in a higher fluctuation rate. One could therefore think that the increased fluctuation rate would impact the number of prefixes the root server is capable of announcing, but apparently it does not. The second filter configuration, which applies filtering of prefixes that are not announced by any peer, resulted in almost 3 times more announced prefixes when compared with the first filter configuration that does not apply filtering of prefixes. Additionally, the trend holds true even for the number of prefixes that has been installed at the root server, where the third configuration consistently reported to have installed more prefixes than the first and second filter configuration. However, the reason for this behavior remains unknown, but it can potentially be a consequence of the increased fluctuations for the second and third filter configuration, where the root server needs to queue up a bigger set of prefixes to announce, leading to that more prefixes reaches the peers in each BGP update. In our results, it is reported that a maximum of around 15 million prefixes was announced by FRRS. On a peer-by-peer basis, this results in that each peer received 625,000 prefixes from FRRS. Moreover, in January of 2021, it was reported that the complete IPv4 BGP routing table grew by 6%, year-over-year, to a total of 860,000 prefixes. This means that to announce the complete BGP routing table in our benchmarking environment, FRRouting would require more than 180 seconds to complete this task. However, according to the Amsterdam Internet Exchange, a neutral member-based association that operates multiple interconnection platforms around the world, their root servers hold around 255,000 IPv4 prefixes in the master routing table. These prefixes are the best routes that the BGP path selection algorithm has selected among all received routes from all the established BGP feeds. Additionally, they advises its members to configure a max prefix of 320,000 for IPv4. What this means is that far from every root server advertises the complete BGP routing table of 860,000 prefixes. According to the information given, our research shows that FRRouting is more than capable of meeting the requirements that some of the world's internet exchange points may have. How can we improve our method? To begin with, one could consider using multiple FRRouting instances instead of emulated BGP peers. This may result in that more prefixes are announced towards the root server, putting more load on FRRouting. It could also be good to connect the servers through a physical switch instead of a virtual switch, which may result in bottlenecks. Something called software tracing may give more information about how FRRouting functions. Further dimensions to research include looking at how path filtering impacts the performance of FRRouting. Is it more computationally heavy? BGP is critical for the internet infrastructure. Understanding the performance of BGP implementations is therefore key for a well-functioning society. In our benchmarks, FRRouting shows limitations when announcing prefixes on the network. Fluctuations are higher when applying filtering of prefixes. FRRouting still announces way more prefixes than what's in an average root server's routing table. Future research may develop a more realistic environment with other tools for recording data. Thank you for listening.